here. This red curve is the graph of y equals x to the 2/3 power. The blue line is the graph of y equals 4. I've only shown it from x equals 0 to 8. And so this region, this graph is symmetric about the x-axis. So we could actually just find the volume of the solid from 0 to 8 and double it, which is not what I've shown here. But this blue line right here represents a typical diameter of one of the cross sections. And that's what we mean by whose cross sections are semicircles with diameter on the base. So that diameter for each x as we move along the x-axis from 0 to 8 can be represented by 4 minus x to the 2/3. So for this x right here, this distance is x to the 2/3 power. And so if I want the distance, the length of the diameter, it's the top y coordinate minus the bottom y coordinate. If that's a diameter, the radius is half of that. And the area of a circle with that diameter is pi times the radius squared, but our cross sections are semicircles. So we want to take half of the area of a circle, and that's where this 2 came in. And then the volume of the solid created will be the definite integral from -8 to 8 of the area of the semicircle, which is this formula right here. So you'll have to square that, probably pull out some constants, find the antiderivative, and evaluate. So just so you can see what's going on, whoop, I'm going to, what did I do there? Share screen is what I meant to click. Go to Desmos, and here's the graph. And you can see if I let x of 1 move this way, those are our typical diameters. And if I enable this g function and this function right here, that green semicircle represents the cross section for the given x value that I'm on. So we would expect as we move along the x-axis from 0 towards 8 that these semicircles would start getting smaller, and that's because the diameters are getting smaller. So right now the area of this first cross section is, well, the diameter is 4, the radius is 2, so pi times 2 squared would be 4 pi, but half of that would be pi, 2 pi, which is 6.28. Okay, so as I move along here, there's a typical diameter, there's a typical cross section. You can see that the cross sections are getting smaller and smaller until we get to x equals 8, it disappears. Okay, so that's what's happening. You have a choice of setting up the definite integral from -8 to 8, like I did here, or you can say it's twice the integral from 0 to 8 of the area of the semicircle, dx. Okay, and I'll let you work on evaluating the definite integral. There you go.